In the next part, we have a source-free parallel RLC. So we still have source-free, but it is parallel, no series. The only difference here is what? In series, we solve for the current. In parallel, we solve for the voltage. And of course, there is a reason for that. The reason is how we create the equation for the circuit. And here, this is the equation here. You see the equations are very similar. If it is overdamped or critically damped or underdamped, you still have the same equation, but for voltage, not for the current. So how we come up with this value? Why it is voltage? Why it is not current? Why alpha look like this? For example, alpha and the other one R over 2L. Here it is 1 over 2 RC. So how? Let us see here. What we have to do here is that we calculate or create equation by using Kirchhoff current law. We say this current plus this current plus this current equals 0. And the current here is V over R. The current in the inductor is 1 over L integration of V dt. And the current in the capacitor is C dV by dt. So to get rid of this one here, you have to differentiate all the whole equation and then divide by what? Divide by C. Why we divide by C? Because in this case, this will be the highest derivative. This term will be the highest derivative because we differentiate the whole equation. So it will be d square V by dt square over, and here 1 over RC dV by dt, 1 over LC dV. So if we replace this by 2 alpha and this one by omega 0 square, then in this case, alpha equal what? Equal 1 over 2 RC. This is the difference between parallel and series. Alpha is different, and here we solve for the voltage. The other one, we solve it for the current. And then the equations will be exactly the same. There's no difference. All what you have to do is just find the initial conditions and find A1 and A2. And here, the initial conditions are for the voltage, V of t. So we need V of t, V of 0, and dV by dt. So for example, if we have a circuit like this, and this is L is 1, C is 0.25, we need to find the response and the equation, which is the same here for V of t. If R equal to 1.5, then we just need to create a table like this, R2, 1.5, L is 1, C is quarter, and then use this equation to calculate alpha, 1 over 2 RC, so you can calculate these values, very easy. And then omega 0 is square root of 1 over LC. Then you compare alpha with omega. If alpha is less than omega, it is underdamped. If they are equal, critically damped. If alpha is more than omega, it is overdamped. And depending on what kind of response here, you have the equation. If it is underdamped, this is the equation. And you need to calculate omega d. Omega d is the square root of omega 0 square minus alpha square. And you have alpha already. And if it is critically damped, this is the equation for the voltage. And if it is overdamped, this is the equation for the voltage. And you just need to calculate S1 and S2 using this equation here. Here's an example, one of the circuits that we solved in the initial condition part. If R equal 170.71 and 50, so how would you solve this? We solve it using the same method. First, we need to decide the initial conditions. If you don't know how to find the initial condition, you can ask me, or you can return back to the initial condition part, because this problem is solved in the initial condition part. So this is the initial condition for the voltage and for the derivative of the voltage, V dot. Then we create a table, R equal 170.71 and 50. L is 0.4 Henry, and C is 20 microfarad. Remember this 20 micro, so it is 20 times 10 to the power of -6. Okay, so and you calculate alpha using this equation, 1 over 2 RC, and omega 0 is 1 square root of 1 over LC. And then you compare alpha with omega the same way. Here, alpha is less than omega, then it is underdamped. Then this is the equation. Calculate omega d. Here, they are the same. then use this equation. And if alpha is more than omega, then this is the equation. Sometimes you may find, for example, especially in the critically damped, and if this is resistance, you may find, for example, that alpha is almost the same like omega, but not exactly the same. But we assume that they are the same. Like, for example, if this one is 354.1, this is 354.2. So we assume that they are the same. Okay, approximately they are the same. Then the next step is to use the initial conditions, which are dv v of 0 and dv of 0 by dt, to calculate a1 and a2. And to make it easy for you, I did the same here. I prepared these equations for you. So here v of 0 is just 1 as a1. So you just, v of 0 is here. Okay, is 40 times r over r plus 30. So you calculate v of 0. This is a1. Then you substitute here by a1, and alpha and omega d. So what you need to do is just calculate a2. And what's a2 here? You have here dv by dt at t equals 0 is 0. Then you substitute by this value here in this equation, and then you calculate a2. Same for this one here. When r equals 70.71, which is critically damped, then you use this equation to calculate a1, and then you substitute here to calculate a2. For the overdamped, you have to solve two equations into unknowns. Okay, and this will be the last problem in the assignment. I believe you will not find the solution in the handouts, but the solution is here. These are the initial conditions for this circuit: R equal 1.25 and 0.1. This R, and this switch was open after a while at t equals 0. Then the initial condition v of 0 is 0, dv by dt equal negative 20. You can also see the solution in the previous part, which is the initial condition for the same circuit here. And then you create this table. Again, this is R 1.25.1, L is quarter, C is 1. And then you calculate alpha using this equation, 1 over 2RC, and omega 0 using this equation. Then compare alpha with omega. Here, when it is less than alpha is less than omega, it is underdamped. This equation for the voltage. When they are the same, 2 and 2, this is critically damped. When it is more, this is overdamped, and this will be the equation. You need to calculate S1 and S2 using this equation here. Then you use the initial conditions to calculate A1 and A2 using the ready equations which I prepared in the handouts here. Okay, so for R equal 1, there is the equation, and A1 equal V of 0, dV by dt equal omega d A2 minus alpha A1. So the only unknown here is A2. Same here also. Here you calculate A1, and here you calculate A2. For overdamped, you have two equations into unknown. So this will end this part of the source-free series and parallel. You need to solve these two problems for a series. Of course, this problem. We solved this already. We solved both of them, but these are the problems that the solution, you will find them in the handouts. Here you have a series connection, and again this one also series connection, and here you have parallel connection. So you need to submit this or solve this assignment and submit it. Make sure that you solve it right. Next part will be step response, which is RLC circuit with the source, which we call it step response.